In this episode, I sat down with Keith Holdaway, a veteran geophysical data scientist with decades of experience applying analytics and machine learning to subsurface workflows. Keith walked me through a Python Streamlit prototype he's built to identify bypass pay opportunities in mature brownfields, and I thought this was a great example of how AI can integrate multiple data types and screen opportunities before proposing any new wells. Keith showed me how his workflow uses clustering to group wells with similar petrophysical and production signatures. It also uses an AI prediction engine to spot zones of untapped potential, and even an AI agent system that replicates atypical subsurface workflows. All right. Thank you, Keith, for coming on. It's a pleasure for me to be talking to you, and we're going to be talking today about bypass pay. So tell us, what is it that you're going to share with us?
Well, thank you anyway for introducing me to CrowdField and inviting me today. So today, I'm just going to look at an end product, a solution that we developed in AI Python generation. And essentially, what we're trying to do is identify potential bypass pay wells. And so bypass pay essentially is just refers to those hydrocarbon-bearing zones that were either missed during initial development or intentionally skipped. Sometimes that happens because of technological or economic constraints at the time. So what we need to do is think of it from a perspective of, say, a C-level guy who sees it as low-hanging fruit that previous kind of generations of geoscientists or engineers knew was there but couldn't economically develop with the technology available. So this solution is kind of like a dashboard into a brownfield, existing wells that have been drilled, but we're looking for that bypass pay. We're looking for the extra hydrocarbons without actually having to redo seismic or drill new wells or re-engineer the field in a more expensive way. So the industry, I think, estimates that in many of these mature basins, bypass pay could basically represent 10 to 20% of the original oil in place. So say for a typical 100 million barrel field, that's 10 to 20 million barrels we've already paid the exploration costs for. And it's just sitting there waiting for the right technology to unlock them. So this is kind of like a dashboard or a view into that world where we could potentially identify some bypass pay. So let's look at this dashboard initially then. So what we're looking at here in that overview area, we see we have 1, 2, 3, 4, 5, 6, 7. So this is essentially a prototype, one of our first prototypes. We've extended the functionality and features beyond this using, I'll mention some of the things that we've done in the future later, but in this kind of overview, this is the first tab essentially, and it's like the executive war room, if you wish. So a C-level guy could come up in the morning, look at this dashboard, and in a very short time, they can see the entire field's health. So your total wells, the count of high potential bypass pay targets. We identified here 14 potential bypass pay wells. And by the way, this data set is a pseudo data set. I'm not using anyone's data from any company. This is kind of based off of some generated data we use from Gen AI. And so what we're looking at here is some really good, on the left-hand side, you can see the fascias distribution. And if you noticed up here, the number of clusters. So what we do, we cluster all the data, all the wells that we have, all the information, all the well logs, in order that we create a single cluster where a lot of the values across, say, density, sonic logs, porosity, permeability, these kind of petrophysical parameters have a very similar or a smaller range of values. So that will be put into one cluster, and we use a kind of k-means clustering technique to do that. And then within those clusters, we identify a representative well. So we're doing 4 clusters here initially. So you can see the 4 different clusters and what kind of fascias it is, at the depth to the top of that particular reservoir, and the number of barrels per day. And the well 45 will be the representative well for cluster 0, and 47 for cluster 1, etc. So if you look down here at the field visualizations, you can see well locations colored by cluster. So the cluster 3 would be all the yellow ones, etc. And the bubble size, represents a porosity. And so that enables us to see some of the high bubbles and which cluster essentially those high porosity wells fall into. And then when we look at some of the other visualizations, the parallel coordinates plots, this one here kind of answers some of the petrophysical parameters and which clusters some of those wells fall into. So obviously we're looking for higher porosity and permeability and lower water saturation. So you can see some of the cluster 3 wells fit that kind of framework. And so it's important to just for executives and geoscientists to take a quick look at some of these insights. And so at the bottom, we see the kind of decline curve analysis type stuff. And this is basically different clusters and the representative wells. So you can see this red one is cluster 3, well 33. So we're looking here at the kind of decline curve of that particular well in that particular cluster. So when we go into the next tab, the production analysis, this is the kind of like the engine room, the production tab. So this is where I would say theory meets reality. So sea levels can use this to validate the production potential they saw in the overview, and they can track actual decline curves of representative wells. So here we're looking at a selection of different clusters, and I say we have 4 clusters, so we could look at cluster 2, and you can see it's running, and we can see which well is representative of cluster 2. Then you can see the decline curve, where 29 well within cluster 2 is the representative well, and the other particular wells in that cluster, you can see the decline curves there. So it's really about de-risking the investment. So for the asset team and geoscientists, this is their forecasting lab. Essentially, by analyzing production by cluster, they can answer critical questions like, if we drill a new well in this sweet spot, what type of decline can we expect? What's the estimated ultimate recovery? And so this tab moves the conversation from this looks good to here is a validated production profile we can bank on, essentially. Sometimes we customize this because we get feedback saying we don't need this visualization, we need that visualization, etc., and we need different tabs. So this, as I say, this is just really a prototype of the first one we put out. So in the third tab, it's like the well analysis. This is, someone's called this like a digital twin for geoscientists. So this tab is a deep dive diagnostic tool on a single well. So here we're looking at well 33, for example, but you could basically go through all the wells that we have. We have 60 wells, as you saw on the overview. And so then we're looking at the different properties within that well. And so you can see the production history of that well. You can see some of the facies information, which cluster it falls in, the total depth to the top. And you can see the bypass pay potential, net thickness, some of the petrophysical parameters in there. And then we have this normalized radar chart. So this normalized radar chart provides, I'd say, geoscientists with a quick, comprehensive visual comparison of key reservoir properties for individual wells. So here, basically, we're looking at well 33, and you can see this really nice shape. And so some of the wells won't have that shape. So that shape is important because it tells you that well 33 is a pretty good well. If you go, say, to well 2, you don't get that kind of nice shape. So essentially, it's not a bypass pay potential. And so you can go through different wells and build up a kind of a list that you want to prioritize of wells that perhaps within your brownfield you may want to revisit and potentially gain more hydrocarbons out of that particular well without actually doing any other types of seismic analysis. Seismic data is brought into this, seismic attributes primarily at the well locations, and of course we have production data, historical production data that we put in here as well. So if we go to the bypass pay tab number 4, I would say this one here is essentially a prediction engine. It's kind of like the core of the AI magic, if you wish. So the first half uses a rules-based system. So the first principles filter that we apply identifies wells meeting classic good rock criteria. So it's transparent, and geologically pretty sound, but the second half is where the AI truly shines. So this one here, if I do a full screen on that, this shows you the bypass pay potential map. So of all the wells, 60 wells, we've identified 14. These are the green ones that have potential bypass pay. And you can see which cluster they fall in, and eventually, you know, some of the important parameters like porosity, since that's the size of the actual bubble. And then we have just some bypass pay details. So we're looking at the different well IDs for these 14 different wells that are bypassed. And then the top of the depth, what kind of facies we're looking at, the porosity, permeability, water saturation. So this gives you another understanding of what the 14 wells that have been identified by this solution could potentially give you. And so in the second pass, what we're looking at here is an opportunity to actually go in, and let me show you this select new location coordinates. So right now we're looking at a coordinate where the red is, this is at X coordinate, Y coordinate, right? So this location is giving you, we use right now, we don't use a Kriging method on this prototype, but we have been using Kriging and variograms to do a proper type of interpolation, extrapolation between wells, but this one is just using a k-mean, so the nearest well essentially to the coordinate that you've selected. So if you changed, for example, the coordinates that you're interested in, because you think from your previous maps on the previous pages, you can see that it changes here, and this is now the location. And you can use nearest well properties. So these are the nearest well properties, and then you know, as I mentioned, we're using the nearest neighbor, but there is a Kriging technique. And then we go down using that information from that selected location. And what we're doing, we're using the nearest well properties over here, and then we're just using those as our input. But we can actually customize the properties as well. And you have this sliding bar that allows us, if you know, from example, you've done your own Kriging method or something and you picked a location, you may know from maybe using a neural net on seismic attributes, for example, you may have generated petrophysical parameters between wells through another algorithm, and then you can feed those in here, and then that would rerun and tell you. At the bottom, it gives you, then you do the predict potential, and at the bottom, it will tell you what kind of potential we have, limited potential. So we generate this quality score for every well, and it tells you the facies and the depth. And so this kind of information is basically given to the C-level or the decision makers, and their idea about what is a moderate standard cost and what is the quality score reference can be customized to each customer. That can vary somewhat. So we just give them the number that we've generated here. And then in the bypass pay map, this is like an interactive play fairway map. So think of this as a way where it takes the static maps of the past and makes them more dynamic, essentially. So both executives and geoscientists can use this to visually identify sweet spots and trends. Again, this is the bypass pay analysis map. Remember, we've got 14 potential bypass pay locations with a porosity, but over here, you can change that and say, okay, I'm interested in the different facies and size the wells by porosity. And you can see that the main facies is the red, where we're interested in a bypass pay. So you know, you could take out that and that and that. And now you have what we saw before, the bypass pay analysis map, those wells that we predicted within this solution. And it looks like most of them have a facies of clean channel sand. So that gives you the option. You may look for top depth with porosity sizing, or you could say net thickness. And so this kind of gives you an idea around where are the sweet spots within my field. And you have an XY location, so you have the coordinates of the wells within this. And so that enables you to interactively identify, maybe we need to re-engineer a particular workover on a particular well that's been identified as a bypass well that's already been drilled, but we've kind of left hydrocarbons behind, or there is bypass pay, and it tells you the top of the reservoir. It does a reinterpretation of the seismic data. And that's one opportunity there. Or you can actually use the Kriging methodology and actually identify a new location, which would mean perhaps drilling the well. But again, this is more a tool, because you may want to go back to your seismic data and reinterpret areas that you think, according to this dashboard, the X and the Y coordinates are saying it should be at this location. If you have a 3D seismic data set, then you want to maybe look to see, because if you have a homogeneous reservoir, or you have a lot of heterogeneity and you have a lot of structure, as opposed to these more kind of smaller, subtle traps, as opposed to an anticline or something. So again, this thing is trying to analyze using the inputs from production data, obviously, and well data at different locations with seismic attributes at those locations, and those are petrophysics at those locations. But what happens in between those wells, that's where we use some geostatistics to do that, to identify potential bypass pay locations. In the AI agents, this is essentially an automated subsurface team, essentially. So we have a multi-agent technique. And what we try to do, we have 3 agents. One is a data wrangler agent, who validates the data, cleans the data, and does some feature engineering, generating new features like reservoir quality index. We have a predictive modeling agent. So this is just a machine learning technique for bypass pay prediction. We tested several supervised techniques like random forest, gradient tree boosting, neural nets, etc., and tried to come up with a model based off of the data within each of the different customers' location, geology, depositional environment. That would be the ideal, because sometimes it's a random forest classifier and sometimes it's a gradient tree boosting or something like that. So then we need to make sure that we're using the right predictive model. And then there's a well recommendation agent, which is more around the economics and understanding the analysis of the economics and how much it would cost if, and some of the drilling recommendations offset to some existing wells, or do you go back and work over another well. So this would basically run the full agent simulation, where you're looking at those 3 different agents. So this is what we would call agentic AI, I suppose. So we're looking at obviously the 60 wells that were processed with 3,600 records, 0 data quality issues. So it does imputation and it does some scaling within the data as well. And then it creates through feature engineering. Here we got reservoir quality index, which could be very important as we go forward. Because I've run it a couple of times, that's why you see a lot of those. I'll have to change that out. And then you see the model performance. Obviously, the model performance is how accurate this particular model that we're using to do the prediction. And this one has a 94% accuracy. And it tells you some of the statistics behind it. So to measure the validity of the model, whether it's over kind of or under kind of, I'd say, whether it's a good model is essentially what I'm trying to say. Or so we have generated some different scores across that. And it tells you the 10 most important features for the bypass pay prediction algorithm that we're using. And obviously production potential, net thickness, net growth, but we have porosity and permeability in there, less so resistivity and gamma ray and bulk density logs. And then we have this distribution of predicted bypass pay probabilities. So again, it's kind of like a Boolean, but it's more kind of fuzzy logic, where you have 0 basically is 39 wells basically will not have bypass pay probability. Over on the right hand side, we have 8 really good candidates that have a probability of 0.95, and then across that, so it's kind of skewed to the left, which kind of insinuates that this data set has more non-bypass pay probabilities than bypass pay recommendations. And then it comes up with the top 10 recommended wells. So within that, you can see what kind of fascies you're playing with here, and the well IDs, bypass pay probability. So again, you can prioritize your focus for some of the sweet spots and some of the important areas within your field that has a high probability of bypass pay being hit. And some of these features that we've also generated, like an economic score, the top of the depth, top of the reservoir at that location, the net thickness, and some of the other porosity, permeability, other petrophysical parameters as well. And then it gives a kind of executive business summary, and total bypass pay wells, 13 success probability over 50%, and then recommended next steps. This is essentially a spatial distribution for some of the bypass pay, and it kind of prioritizes. So it's saying, like, if you're going to really address bypass pay, this is the location, the XY location, rank 1 as one of the best bypass pay. Probability is 98% within a clean channel, sand, and it's in cluster 3. And then the lowest one, this would be ranked 10th. So, so again, it has potential for bypass pay, but you may want to focus on the top 4 or 5 based off of this particular recommendation. And then the last one is just exporting a lot of different types of data that are generated. And obviously some of the data is input, and then it generates and does feature engineering and creates more data. And then obviously with cluster analysis, it does representative well. So you can download these as CSV files essentially. And then I believe on the Mac, it comes out as a numbers. So these are the representative wells in the different clusters and the selection timestamp, for example. So you can download all that different data, and then go back and review this. So that's essentially a quick pass through the landscape of this particular dashboard. I don't know if you have any questions.
Well, thanks, Keith. I mean, that is a very comprehensive overview. There's a lot into this stuff, man. I think I really like what I'm seeing. It's clean. It's a logical, sequential progression through those steps. We might need to come back to talk in detail in future sessions about those agents, for example. I mean, I'm very interested in the nitty-gritty of a few of these things, but there's a lot here just in the way of compiling information, visualizing, and interrogating our data. For example, those well clusterings and the representative well or the type well, that already there, it's a type of utility that you would find in a spot fire of sorts, for example. It's already a lot of value just in the way of interrogating and visualizing data before even any predictive capability. So I really like that. If we go to the core of the magic, is there a fundamental distinction when we talk about bypass pay between what is a well underperforming in a specific zone versus the identification of a zone that hasn't been perforated by the well versus an area that has been poorly drained by the existing well pattern, so you have an opportunity to drill an infill well in the area? So there are kind of 3 separate things. Is there any fundamental distinction into those 3 buckets?
Yeah, so like you see here on this particular visualization, obviously these are all wells that have been drilled before, right? And so what is done on this particular part of the analysis is identified which of those 60 wells in your portfolio across drilled wells within that field, which ones have potential bypass pay, right? So you can and sometimes the tops, right? So there's an interpretation again from the seismic data where you may have not identified the top correctly in your initial interpretation or in previous interpretations of your data. So this takes in some seismic data. This is before you put that information into this, right? So this in itself doesn't do the seismic interpretation looking for the tops, but it takes the clusters out of here, and then it looks at what it does, it looks at the representative well within that cluster, and then it does a reinterpretation of that representative well for the tops. So again, what is not in here is what is in the kind of production version of this is the geostatistical side, where we have a lot of location information through wells and seismic attributes generated from the seismic at that well location. and petrophysical information, because some of them are cored as well. So sometimes we do a neural net to try to interpolate that between the wells and create pseudo cores at the wells that haven't been cored, or pseudo well logs that haven't been collected at that particular well location. So that kind of is in the background outside of this dashboard, where you're trying to bring in that kind of information. That kind of data set will be input into this, so that then you're looking at bypass pay within existing wells that you can then go back to with a reinterpretation. Maybe it's a bit deep at the top of the reservoir. And then you can also do the inter-well interpolation using variograms and kriging techniques that are pretty sophisticated, and that would be outside. That is an application that is kicked off into production version outside of what you're seeing here. And then as you go onto that map, if you remember that kind of map that we have here, this is actually, right now, I can only change these coordinates in this prototype by actually typing in the X and Y coordinate. Then it changes it and it finds the nearest well, and it uses a K nearest neighbors technique. It's not using any kind of kriging technique. So, potential enhancement, which we have, is just physical interpolation, where we use this Gaussian technique. And obviously with kriging, you have much better, you can quantify the uncertainty much better of whether that location is a good location for bypass pay, because you haven't drilled that location before. And that would be more interactive. So you could drag that star over here. And from the XY coordinates, you can then look at your data set and your seismic. And I think sometimes it's reinterpretation, or it's quantifying the petrophysics at those locations, the porosity, permeability, what is the water saturation and stuff like that. Resistivity, and you can get that information either through other kriging techniques, or some companies already have done some AI techniques for interpolation between wells for petrophysics across the whole. Depends, again, like in the Middle East, in Muscat, we found there's a lot of homogeneous layers within, and they're pretty kind of like railroad layers. Whereas in some of the areas within North America, like in the Permian, you're looking at shale, and that's pretty flat lined where horizontal wells. But you could go into the North Sea and you've got a lot of structure, and so that becomes a little more difficult. So this is just a tool to enable you to kind of find sweet spots. I wasn't sure what your third category was. Did I?
Perhaps in the way that I see how this is calculated, perhaps that includes 3 separate buckets. One is to propose zones that haven't been perforated in the wells. So you can go back to those wells and perforate an additional zone and tap into that potential. Right. Another one is zones that have been perforated by the performance of that well compared to all the neighbors. It tells you that well, for one or other reason, has been underperforming. So there is a potential to be untapped there if you go and somehow, reperforate or stimulate that well. So it tells you something about that zone. And another one is if a well has multiple zones, it's not just a single reservoir, but many reservoirs.
Well, the magic right now, what you see, doesn't account for that third bucket, because we have come across a customer in I think it was one of the unconventional locations in the United States. And essentially they had this layered cake, multiple reservoirs sitting on top of each other, and they had a vertical well going through. And so they had other types of data sets that would enable them to identify which liquids are coming from which area of that particular suite of reservoirs. And so what you're looking at here doesn't really take account for that, because you're only looking, what it does is an interpretation just for the top of the reservoir that may already have been perforated, but there's still bypass pay there, right? And also at a kind of reinterpretation of that data says that, well, it was underperforming because you didn't hit the reservoir, and the reinterpretation of the data says you need to go deeper by 500 or 600 feet or something like that. Or you may be offset from a well that is an extant well that's underperforming, but through the geostatistics, you can actually find that if you're within, I think it was under 500 units of the XY coordinate, you could find that that is a good location if you have a kind of a homogeneous, horizontal, or very stratigraphic type traps as opposed to big structural traps. That works there as well. But that third bucket is not really addressed here.
Yeah, great, get it. The zones, I mean, separating those two buckets, again, the zones that were not perforated, that mostly should come from log analysis and bringing the structure and the new tops or the top reinterpretation. So you identify zones that have not been perforated versus the bucket, which is underperforming zones, which is mostly to do with production performance analysis, right?
Essentially, what the algorithms we use for extant or existing wells at different locations, the underperforming, you can tell from the map, one of these visualizations where the high performing wells are and which cluster they fall in, and you can look at the petrophysical parameters of those and the top of that particular reservoir, that particular location. And you can look at the underperforming that may be adjacent or within a distance that may be a neighboring well, and you think, why is that underperforming? Is there fault zones, or because we did this with Saudi Aramco, and they use a lot of water-driven kind of artificial lift techniques where they have a WAG system, and so they sometimes have these steep zones in the faults that they didn't identify. So the technique behind this particular will identify those wells where they're underperforming, but perhaps you didn't drilled for the top is changed, right? The top in the initial interpretation, maybe you have to drill and it will identify the top. And then you have that other zone where all you need is basically a workover because perhaps you just didn't perforate at the right, in the unconventionals, or the completion strategy wasn't correct. And so those decisions usually are insinuated as questions through this application, and then you would have to go back to your seismic data and your other information, well logs and production data, and make a kind of probabilistic decision as to whether you need to work over that well, or we missed the pay zone, and so we need to drill within that.
Gotcha. Yeah. Keith, the AI workflows here, or machine learning, if you will, is to do with the fact that there's a lot of data to be analyzed, and it's done fastly by these algorithms. But it's because the data that it's loaded by the user is just raw data. It's the raw logs, is the raw production history. There's no interpreted data coming into this, right? So
that's correct. Yeah. So what it does, it goes through the pre-processing technique. It does kind of like an exploratory data analysis of the well logs, and it basically imputes missing values, and there's different ways to impute that. On the production version, you can actually see some of the pre-processing techniques, and you can select what type of imputation you want, and then you do the scaling and feature engineering. And so you're trying to make a more robust, enriched data set based off of the raw data coming in the LAS files, for example.
Yeah.
And then in the production data, it does decline curve analysis, and there is a time series analysis technique as well, and not just the ARPS equation that we use, but there is a time series analysis that tries to take your production data and then use maybe an ARIMA. We've even been asked, can you use an LSTM, which is a deep neural network, to do because these people, they read their papers, right, and they from different conferences, and they say, well, this guy did a much more accurate history production forecasting using a long short-term memory deep neural network. And so we've been playing with that for a long time, and we've done that, but not within this particular system. This is more kind of just a basic ARIMA type analysis.
Gotcha. Those agents you showed on that agents tab at the top are kind of the ones that are working in the background in the preceding tabs, or this is a tab that shows those agents as a separate standalone products of this suite?
Yeah, so this is only working within the AI agents tab. It's not part of this. This is
okay.
kind of different areas of AI
different
stuff.
areas. Yes, right. Yeah, I would be very keen to come back to you at some point and have a look at those agents.
Yeah.
Is this product meant for both oil and gas, or it's inherently in the calculations tailored for oil only?
No, oil and gas.
Oil and gas. And
Yes.
obviously, it's more useful in developed fields where you have a lot of data, a lot of wells, and a lot of opportunity.
Yeah. So we're thinking of taking it to the next level with real-time data integration from fiber optics and downhole sensors. So that allow us to continuously update our models as new
Yeah,
production comes in.
I was going to ask. So the data load here is basically a one-off at the beginning. It's not this is not connected to any databases.
There's no historian data coming in from real time, and that's
Yeah,
people have asked us to put that in, implement that kind of techniques and abilities to do that, so they can incorporate more advanced physics-informed machine learning that combines traditional reservoir engineering principles of AI, but in real time. So you need like a event stream processing engine that takes like production data as time series and then does an analysis of that. But we've also been experimenting with generative AI for automated reporting and generating alternative development scenarios. So it's like a bot where you can say, show me what would happen if I changed our completion design in this zone, and getting almost instantaneous simulations with economic analysis with that kind of, using the RAG technique.
yeah.
And that kind of large language model could even be put at the end so that you can actually query something that's particular to this field.
Yeah, absolutely. I mean, there's a lot of potential to grow in multiple directions with this thing, man. I'm curious, is this a prototype you're using yourself to provide services to your clients, or are you commercializing this, or are you thinking of commercializing this as a software product? What's the go forward for you here with this?
Well, yeah. So I'm working with a guy I used to work with at SAS Institute, and he's the guy who's helping me kind of build the architecture out. So I took this to Petronas, and we showed the petrophysicists and geophysicists and geologists, and they really liked it. But they had some feedback about customizing it. So we're at the point we feel that we have enough functionality in order to architect a solution stack, and we've looked at cloud implementation using usually AWS architecture, but also Azure, because most of them are AWS apparently. But there's some on-prem stuff, especially we went to Istanbul to talking to those guys, and they just do on-prem, Then we have an implementation roadmap that is about 16 weeks, because we have put this into an unconventional with Shell Oil out in I can't remember the damn name of the field now, but it's out there somewhere in Texas. And so we haven't sold this per se as a product. We're kind of getting to that point where we're going to use a Docker or maybe a Kubernetes and container in order to run this. And we have 2 or 3 companies, Petrobras, Petronas, and Aramco. But it's funny how these companies are all, and ADNOC as well, these companies are NOCs, right? As opposed to, because we went to Shell and Exxon in Houston, and they're like, all they wanted to do was, and according to my experience as well, talking to those people, was find out what you're doing, and then they go away and emulate it themselves, not interested in buying anything.
Yeah, that's right.
Yeah, so we go to the small kind of independent companies. We went to Devon Energy, and they're very interested. So we're at the stage where we feel like we're stepping into that area of creating a solution. We have the architecture. We know how to implement this in someone's architecture, whether it's on-prem or in the cloud, and the data structures and stuff like that. So well databases, people tell about OpenWorks and Petra, then there's a Pi system, OSI soft stuff. So we're looking at the real time as well from historians. So it could be, like you say, it's a lot of fun, right? So you just sort of
Yeah, and yeah, absolutely, a lot of growth potential as well. So the prototype as such is not something that you're open sourcing or giving access to for people to play with. It's just basically a product of yours that you're using to have these conversations with potential
I'm saying
clients. You get that feedback. Yeah,
I talked to Kevin the other day, and he's now working to put this into one of the containers. I think he's using Docker, and we're going to be able to let people access through the web the usage of this, so they can navigate it and play with it and give us feedback. So that will be available with it by, I'd say, January, the first week of January.
Okay, fantastic. Yeah, fantastic. Fantastic. All right, man. I think we're running out of time now. So I have quite a few other questions that I would like to follow up with, but it'll have to be for now.
Yeah, well, I really enjoyed it. Thanks, Alan, for inviting me.
Thank you. Yeah, thank you very much for coming on. This looks really good, man. I think it has a lot of growth potential. Riding the AI wave early on, I think it's just a matter of time, as I said at the beginning with you, man. But yeah, you're onto something here.
Right, there's a lot of opportunities to plug and play into this as well, right? I mean, someone was asking us about fault seals analysis. Can you somehow integrate that into here, so that with the bypass pay for stratigraphic traps, I can do a fault analysis as well? You know, so there's a lot of ways, and you would know as a reservoir engineer better than me. I was a geophysicist, so I was just messing around with wiggle traces, you know, not so much. I've learned a lot about reservoir engineering in the last 20 years of playing with AI, but that's not my background, really.
Well, so I think, man, you're at the right point where you are actually listening that feedback from the big clients, and that'll tell you which direction to go, man. That's exactly that, right?
I will definitely share it with you, Alan, as soon as we can, and then you can play with it. And,
yeah, sounds good, mate. I really appreciate this, Keith, and let's stay in touch.
Okay, take care. Have a good day. Cheers.
You too, mate. Thank you. Cheers. Bye.